Welcome back, guys. In this video we're looking at the cylindrical shell method again, and this time I wanted to show you an integral with respect to y as opposed to an integral with respect to x. So here's our region. It's bounded by this x value as a function of y. It's just a polynomial function in y, and then we've got x as y squared over 2, another polynomial function in y. Super simple. And we're going to take this region and we're going to revolve it about y equals 2. So I'm taking this guy and I'm going to revolve it up here. So we're going to do what we always do. There's 2 and there's 4. We're going to draw the region. And then try to sketch the reflection of the region. This one's hard. At least it's hard for me. Maybe some artists in the class. Much respect. I wish I had that skill. Yeah, that's pretty bad. Okay, so yeah, that's my reflection. That's my attempt at a reflection. Okay, but that's how we always start, right? Just to get a sense of what's going on. I'm taking this and I'm revolving it around. This one looks more organic than others, doesn't it? So we sketch the region and the axis, and then we sketch the reflection about the axis. Now, with this problem, we could do cylindrical shells, or we could do the disc or washer method. Because there's a gap between our region and the axis, I think we'd have to do washers. But I think this is going to be easier if we use cylindrical shells, because look what happens. If we're using the cylindrical shell method, the next thing we do is we slice parallel to the axis. We always slice parallel to the axis for cylindrical shells. So when I slice parallel to the axis, I've got a slice that looks like this, and then in the reflection it's going to show up on the other side. It should be the same size, but my reflection's not that good. Okay, so we slice parallel to the axis, we draw the representative rectangle, and we rotate it around. Revolve the representative rectangle about the axis. So when we do that, we're going to see this over here, and roughly it's going to look like this. Now you might be saying, I don't really know that looks very simple, but notice that the height of the shell, instead of being up and down this time, that height is going to be x on the right minus x on the left. It's a horizontal distance, and that is a good thing. I want x on the right minus x on the left, because look at these equations. I've got x as a function of y over here and x as a function of y over here. If I want to do x on the right minus x on the left, all I have to do is take that one and subtract that one. If I were doing something where y needed to be a function of x, that would be more challenging for this one. Who wants to solve that for y as a function of x? I mean, it could be done. I guess we could complete the square on the y squared. There would end up being a couple of different square roots. Like, it would be a mess, but we could do it. But this is going to be much nicer. It's just going to be this function minus this function for the height. So I'm going to use the cylindrical shell method for this because I think it makes the most sense. If you are like, I'm not really sure, try it the other way and see if you can find y as a function of x. It can be done. It's just a little bit of algebra, and I think this is much simpler. So we sliced parallel to the axis because we're using cylindrical shells. We drew that representative rectangle and its reflection, and then we also sketched a representative shell. It does not have to be perfect, it's just a sketch, right? Okay. So now I want to take my shell and I want to find its volume. So I'm going to slice it down one side, like it's a seam on a can of beans, and I'm going to unfold that. I could unfold it this way, but I'm going to unfold it and rotate it so it's still like this. That's how I'm used to seeing it. Now this distance here, that's the width of my shell, is the width of that representative rectangle. The width of my rectangle is delta y, so everything's going to be in terms of y. And then my height, that's the height right here. I know it doesn't look like a height because it's left and right, but that's okay. That's the height of the shell. It's horizontal. The height is right there. That's going to be this height over here. And then this distance all the way around is the circumference. And that's 2 pi r. Same thing. All right, so volume is 2 pi times the radius, that's the circumference, times the height, times delta y. So all we need are the radius and the height in terms of y, and then we'd be good to go. Okay, now you have to go back to your picture, go back to your original picture, and label the radius and the height. One of them is going to be vertical, the other one's going to be horizontal. That will always be the case with cylindrical shells. Height was left to right, or yeah, I said left to right. The height is horizontal. So it goes from the left to the right. So if I want that distance, I've got to take the larger x value and subtract the smaller x value. So that's x on the right minus x on the left, because if x equals 10 is over here, all the values of x that are less than 10 are farther to the left of that. So I want to take the large x value, which is x on the right. I'm doing this now, and I'm subtracting x on the left in terms of y, because this is the delta y integral, okay? Or it's going to be a dy integral when we're done. X on the right is given by this equation up here. X on the right is y squared over 2. We're talking about the ith height, so I'm going to put a little I on that. X on the left is the x value on this curve as a function of y, so it's given by this equation, because that was our rectangle. There's right and left. So on the left, we're on this 4th degree polynomial. So we're subtracting x on the left, which is y to the 4th over 4 minus y squared over 2. And that actually simplifies quite nicely. I'm going to distribute that negative. You see the y squared over 2 minus y to the 4th over 4 minus a minus is plus. Hey, I got 2 of those, so it's just a y squared. So I've got y squared minus y to the 4th over 4. And little i's are just there to say it's the height of the ith cylindrical shell. So the height is y sub I squared minus 1/4 of y sub I to the 4th. Dividing by 4 is the same as multiplying by 1/4, right? So we're good. It's the same thing. Now the radius, that height was horizontal, the radius is vertical. Careful, if it's vertical, that's the top y value minus the bottom y value. The top y value is given by that axis, the equation of that axis. Y is 2 up there. The bottom y value is just y. And our students will say, why? Why is it just y? I don't understand. Well, remember, if we're at a general point, x, y, the distance from there to there is y. The distance from the x-axis to that point is y. The distance from the y-axis to this point is x. So if this was 2, 3, this would be 2 units in the x direction and 3 units in the y direction, right? You can say, how does that make that y? Well, the distance from here to here is y. And the distance from here to here is 2. So what does that distance have to be? Well, it has to be 2 minus the y. Or I'm taking 2 That's the y value up here on the top, minus the y value down here, which is just y. So you can think of this as all being 2 and that being y and that being 2 minus y, or you can think of that as 2 minus a y, and the y is that distance there. So we've got y on the bottom is just y sub I. So our radius is 2 minus y sub I this time. All right. So we're going to take the sum of those, take the limit as n goes to infinity, the number of shells goes to infinity. It's going to give us the volume. I'm going to skip that step this time. We've done a lot of Riemann sums. So we're just going to have the integral of 2 pi times 2 minus y times y squared minus 1/4 y to the 4th. In the limit, delta y becomes dy. And we are integrating over with respect to y. So y has to start here and stop here in our original region, not the reflected region, but the original region. So we start at y equals 0 and we go to y equals 2. And this represents the volume of that solid of revolution. Now, in order to evaluate this, I can't just take the integral of that and take the integral of that and multiply. It doesn't work that way. There is no product rule for integrals. What you've got to do instead is factor out that 2 pi and then distribute 2 minus y times that quantity. First times first is 2y squared. Outer times outer, it's going to be negative 1/2 y to the 4th. Inner times inner is negative y cubed. And last times last, that's a negative times a negative, that's a positive 1/4. Y to the 1st times y to the 4th, add the exponents, it's y to the 5th, dy. And then we anti-differentiate, bring the 2 down, add 1 to the exponent and divide by the new exponent. Bring the 1/2 down, add 1 to the exponent and divide by the new exponent. Bring the negative down, add 1 to the exponent and divide by the new exponent. Bring the 1/4 down, add 1 to the exponent and divide by the new exponent. Plug in 0 and 2 and subtract. All right. So my volume is 2 pi times 2/3, and I had 2 cubed minus 1/10 of 2 to the 5th minus 1/4 of 2 to the 4th plus 1/24 times 2 to the 6th. And then I'm going to substitute in over here y equals 0 to everything. That's 0, 0, 0, and 0 this time. Because it's a polynomial, everything cancels. If it's not a polynomial, better check. Now, everything's not going to cancel every time. We get 0. All right, and then if we want to get the right answer, we simplify. That's 8 times 2 is 16 over 3 minus 32 over 10, or factor out one of those 2's, 16 over 5. And then I've got 1/4 and 2 to the 4th, so it's going to be 1/4 of 16, or 4. And then 2 to the 6th, I can write that as 2 to the 4th if I divide this by 4 as well. So I've got, when I divide by 4, I get 6, and then I've got 2 to the 4th over 6, so 2 cubed, get rid of one of those 2's, one of those 2's, so we're going to have 8 over 3. Okay, you can always use your calculator for arithmetic, guys. I've got 16 over 3 plus 8 over 3, that's 24 over 3. 24 divided by 3 is 8. And I've got 8 minus 4 minus 16 over 5. So that's 4 minus 16 over 5. 4 is the same as 20 over 5. Subtracting 16 over 5, that's 4 over 5. Times 2 pi is 8 pi over 5. Woo, all that. Yay, arithmetic. For this, that many units cubed is the volume of this solid of revolution. Okay. Now let's do one more. So suppose this is your region. This is the curve given by x equals 3 y squared minus 2. Oops, not to scale. This is the curve given by x equals y squared. And they both intersect at 1, 1. Definitely not to scale. And we're taking this region and we're revolving it. Let's see. Let's revolve around the x-axis this time. When I revolve around the x-axis, I'm going to see something that looks like this. Oh, that's so horrible. I'm so sorry, guys. Another ugly picture. The question is, do you want to use the cylindrical shell method or the disc or washer method for this? Well, I like the idea of using the cylindrical shell method. Let's use cylindrical shells. So we're going to do this one problem 2 different ways. Once with cylindrical shells and then once with the other method. And that's going to be the disc or washer method. I think it's easier with cylindrical shells, and you'll see why. Okay, so if I'm taking this region and I'm rotating around this axis, we sketch the region, sketch the axis, sketch the reflection, slice parallel to the axis for the shell method. It's always parallel for shells. And that piece, it shows up again over here. Ooh, it's a bad slice. It's because my picture is so bad. And we end up with shells that look like this. Oh my goodness, these are really bad tonight. Okay. So we slice parallel to the axis. We've got our representative rectangle. We've got our representative shell. And notice that the width of that rectangle is delta y. So now we just need to find, after we've sliced parallel to the axis and drawn the representative rectangle and representative shell, we need to find the volume of that typical shell. And it looks like this with the shell method. If I slice it down the side and I unfold it, the height is the distance from there to there this time. So height is this. And the width of the shell is delta y. And the distance all the way around here is the circumference, or 2 pi times the radius. So we know we need 2 pi times the radius times the height times delta y. So we just need radius and height in terms of y. Now looking at your picture, the radius is vertical. It's up and down, up and down. Careful here. Oh, actually, I'm doing it the wrong way. We always want to go from our axis out to the original region, not the reflection. And my original region is up here. So that radius is the top y value minus the bottom y value in terms of y. So it's just y minus 0, or just y sub I this time. And that's what's going to happen every time you use the shell method and rotate around just the x-axis. You're just going to get y. It changes a little bit if it's another horizontal line. It's going to be y plus or minus something, or something plus or minus y, depending on where that axis is relative to your region. But if you're just revolving a region that's above the x-axis, below the x-axis, you're just going to get a y. Okay, and now the height, I marked it here, but it's really this distance up here. It's x on the right minus x on the left. And actually it's nice, it was given to us. X on the right is just y squared. Put a little I on it for the ith shell. X on the left is the x value on this curve as a function of y, and we were given that as a function of y, so that works out. So we've got that. So we can simplify that because we've got y squareds everywhere. So you've got a 2, and one of these minus 3 of them is minus 2 of those. So that's our height, 2 minus 2 y sub I squared. All right, so that's enough to write down our integral. This is 2 pi times the integral of y times 2 minus 2y squared. Delta y becomes dy in the limit, and we're integrating from one y value to another. Always look at the original region. Y starts at 0 and goes to 1. That wasn't too bad. Now to evaluate this integral, I might factor out the 2. Factor out the 2, I'm left with this. Took 2 out of both of those. That 2 times this 2 pi gave me 4 pi. Now you've still got to distribute this y. Y times 1 is y. Y times negative y squared is negative y cubed. And then you anti-differentiate using the power rule. Add 1 to the exponent. Divide by the new exponent. Bring the negative down. Add 1 to the exponent. Divide by the new exponent. Evaluate from 0 to 1. At 1, you just get 1/2 minus 1/4. At 0, you just get 0. 1/2 is 2/4. 2/4 minus 1/4 is 1/4. So it turns out the volume is pi. Isn't that nice? I love pi. I love the mathematical constant pi. I love actual pi. Oh, that's really fun. Okay, so we've got this over here. That's the volume. That's the cylindrical shell method. It only took one integral. Now let's think about finding that same volume using the disc or washer method. So I still have x, or I wrote y, x equals 3y squared minus 2, and x equals y squared right here. And we're still revolving it around the x-axis, so that hasn't changed. And I'm sorry for my bad graph. All right. So I sketch my region, I sketch my reflection, my poor reflection. Yeah, that's really bad. Okay, this was the original. Now remember, with the disc or washer method, instead of slicing parallel to that axis, which would be like horizontally, we're going to slice vertically. Notice I have discs over here. There's no gap between my function and the axis for x between -2 and 0. But once I get past 0, all of a sudden there starts to be a growing gap in the middle. Things change a bit. So I'm going to have to do 2 integrals here if I use the disc or washer method. I'm going to have one integral from here, from -2 to 0, and those are going to be discs. And then I have another integral from 0 to 1. those are going to be washers. But we should still get pi when we're done. So yeah, this will work. We can use the disk and washer method on this one, but we're going to have to do a lot more work. So we sketched a reflection. For disks and washers, you slice perpendicular to the axis. And when you slice perpendicular to the axis, in this case, you end up with disks for a while and washers after a little while longer. So you've got to decide between disks and washers, and we've already done that. So for x between -2 and 0, we've got disks, because there's no gap between our region and the axis. And for x between 0 and 1, this is clearly not to scale, we've got washers, because there is a big old gap between this region and the axis. And then in both cases, the width of my disk or washer is delta x, or if you prefer, you can draw a representative rectangle. The width of that rectangle is delta x, or the width of this rectangle is delta x. Okay, so we decide between disks or washers, we decide between delta x and delta y, we choose delta x. So I'm going to set up the first integral, and then I'll set up the second integral, and we'll add them together, and hopefully we'll get pi. It should be exactly the same volume either way. Okay, so the first integral, this integral over here, volume is, volume of one disk is, the volume of a disk is pi r squared times delta x in this case. We just need the radius. Well, the radius is the distance from here to here, so that's a y value minus a y value. So it's the top y value minus the bottom y value as a function of x. Now, when I am on this curve, I know that x is given by 3y squared minus 2, but it doesn't tell me what y is. That's my top y value. So I'm going to have to take this and solve for y. It's actually not too bad. Just add 2 to both sides, divide by 3. That gets you y squared. Take the square root, and y is positive on this piece. So it's just going to be the positive square root. So the top y value is just this square root of x plus 2 over 3. Put a little I on it. And the bottom y value, that's y equals 0. So we've got pi times our radius squared times delta x, that's the volume of one piece. And when we square it, we get pi times x plus 2 over 3 times delta x. It's actually not too bad. You can factor out that pi over 3, so I've got pi over 3 times x plus 2. In the limit, we don't need the I anymore. Delta x becomes infinitely small. We're going to call it dx, and we're integrating from x equals -2 to 0. And that's going to give me the volume for the first piece. Ooh, I guess I need to be careful here. For x between -2 and 0, oh, I think it's going to be fine. Yeah. -2 plus 2 is going to be 0. -1 plus 2 is going to be 1. I was worried about the sign of this, but it looks like it's going to be positive all the time. So we're good to go. Okay, so that's the volume for the first piece. Now for the second piece, I've got an inner radius and an outer radius, or this inner radius and this outer radius. Remember, the inner radius goes from the axis to the innermost edge of that representative rectangle. The outer radius goes from the axis to the outermost edge of that rectangle. That has to do with this washer, for the washer method. I'm going from, it's the first radius, the inner radius, is filling in that gap. We're going from the axis out to the edge of the gap. So that's going from here to here. And the outer radius goes from the axis all the way out to the edge, because that's the big disc. Like, that's the big disc that we took a hole out of to get this washer. Now these are still vertical distances, so you're going to use the top y value minus the bottom y value for these. I'm going to do all of that down here. So this was that first piece. That was this guy. Now we're on to the washers. So for the washers, I need the larger radius, excuse me, and the smaller radius. Larger radius is the y value on that yellow curve. So it's the top y value minus the bottom y value. And the y value on that yellow curve turned out to be this square root, we found out. Square root of x sub I plus 2 over 3. That was y on this curve as a function of x. And then on the x-axis, y is 0. So we just get that square root. For the inner radius, you've got the top y value minus the bottom y value. The bottom y value is still 0, so we're good there. But now I need a y as a function of x on this curve. It's not too difficult. On that curve, x is equal to y squared. I need to get y by itself though. So y is going to be the square root of x. And y is positive there, so we do get the positive square root rather than the negative square root. So I've got square root of x sub I minus 0, so it's just square root of x sub I. Alright, so the second integral, well, before we go there, the volume of the washer is the area of the washer times delta x. And the area of the washer is the area of the large circle minus the area of the small circle times delta x. You can factor out the pi if you want to. And we just need the outer radius squared and the inner radius squared. And it turned out that the outer radius, the large radius, was that. The inner radius was that. And if we square those, actually simplifies quite nicely. The square root and the squaring function undo each other. We end up with this. Okay, so on this interval from 0 to 1, where we've got washers, our volume is given by this formula. That's the volume of one slice. So I'm going to factor out the pi, the integral from 0 to 1 of this. In the limit, we get all the x's. I'm going to factor out that 1/3 too. So this is x plus 2 times 1/3 minus x. You want to integrate that with respect to x. Whew! So I need to take that and add them together. Hopefully we get pi. So total volume is the integral from -2 to 0 of pi over 3 times x plus 2 dx. And then the next one, we've got this. I'm going to factor out the pi. I think I'll distribute that 1/3 now. I'm going to have 1/3 x plus 2/3 minus a single x. One-third minus 1 is -2/3, so we're going to have 2/3 minus 2/3 x dx. Alrighty. If you want, you could factor out 2/3 there as well. Now let's just anti-differentiate. Add 1 to the exponent, divide by the new exponent. The antiderivative of a constant is constant times the variable. Of integration, this time it's x. Over here, I'm going to factor out the 2/3. And now I've got the integral from 0 to 1 of 1 minus x dx. Okay. I'm trying to save some trees. I go through so much paper. I'm going to use this other sheet of paper that we used for a different problem. Alright, so I've got pi over 3 times 1/2 x squared plus 2x, evaluated from -2 to 0. And then we've got 2/3 of pi times the integral from 0 to 1 of 1 minus x dx. This, if I plug in 0 for x, I get 0. And if I substitute -2 for x, -2 times -2 is 4. So I'm going to have 1/2 of 4 plus 2 times -2. I've got 2/3 of pi over here. I'll work that out in a minute. Antiderivative of 1 is x. Antiderivative of x, add 1 to the exponent, divide by the new exponent, plug in 0, plug in 1, and subtract. So I've got 0 minus pi over 3. This is 2 minus 4. 2 minus 4 is -2. So I get 2/3 of pi for this part. Over here, we get 2/3 of pi. I have 1 minus 1/2 minus 0. So I end up with 1/2 of 2/3 is 1/3 of pi. What's 2/3 of pi plus 1/3 of pi? You said pi. You were right. So cool. We got pi by evaluating this integral, the integral for this piece and the integral for this piece, and using the disk method for this guy and the washer method for this guy. Or 30 minutes ago, do you remember when we did this? It's so much more efficient in this case. And why did it work? Because that right function and left function for the height, there was only one right function and there was only one left function. When we went to disks and washers, I had that outer edge for a while, and I had discs over here, I had washers over here. It just was a lot more work. So I saw I had to have 2 integrals as soon as I went from discs to washers. But either way, whichever one you prefer, you get pi for the volume of the solid of revolution that results from taking this region right here and revolving it around the x-axis.